So here's something you probably haven't thought about today, even though it hasn't left you alone for a single second of your entire life. Gravity. Right now, wherever you are, whatever position you're in, gravity is pulling on every atom in your body. It's pulling on the blankets on top of you. It's pulling on the air in the room. It's the reason you're lying down instead of floating. It's the reason rain falls, rivers flow downhill, and the moon hangs in the sky instead of drifting off into the void. It's the reason the earth is round, the reason the sun shines, the reason galaxies exist at all. Gravity is, in a very real sense, the architect of everything you've ever seen, and yet it's also the weakest force in nature, the most mysterious, the one that even now, after 4 centuries of serious scientific inquiry, we still don't fully understand. And that's what we're going to talk about tonight. We're going to take our time with this. We're going to start way back, long before Newton and his apple, long before Einstein and his curved spacetime, and we're going to walk through the entire story of how humans figured out what gravity is, how it works, why it does the things it does, and why, after all this time, it still keeps surprising us. If you drift off somewhere along the way, that's completely fine. The story will be here, and honestly, there's something kind of fitting about falling asleep while someone talks to you about falling. Let's start with the oldest question. Why do things fall down? It seems so obvious that you might not even think of it as a question. You drop something, it falls. Of course it does. But why? What is it about down that makes things go there? For most of human history, nobody had a good answer, and the best attempt came from the ancient Greeks, specifically from Aristotle, around 350 BCE. Aristotle was a genius, and I want to be careful about how we talk about him, because it's easy to look back from the 21st century and snicker at his mistakes. But Aristotle wasn't stupid. He was trying to build a complete theory of the natural world, using nothing but observation and logic, without any instruments, without calculus, without even the concept of a controlled experiment in the modern sense. And the system he came up with was, by the standards of his time, remarkably coherent. He believed that everything in the terrestrial world was made of 4 elements: earth, water, air, and fire, and that each element had a natural place in the cosmos. Earth belonged at the center of the universe, water belonged just above earth, air above water, fire above air, and every object moved toward the natural place of whatever element dominated it. A rock falls because it's mostly earth, and earth's natural place is at the center. Smoke rises because it's associated with fire, and fire's natural place is up high. It wasn't gravity in our sense. It was more like a cosmic homesickness, things trying to get back where they belong. And here's the part that stuck around for almost 2,000 years, the part that's actually wrong in a really instructive way. Aristotle also believed that heavier objects fall faster than lighter ones. And if you just think about it casually, that seems right, doesn't it? Drop a bowling ball and a feather from the same height, and the bowling ball hits the ground first, obviously. So heavier things fall faster. Aristotle basically said, the speed of a falling object is proportional to its weight, and inversely proportional to the resistance of the medium it's falling through. A rock falls fast through air and slowly through water, because water resists more. A heavier rock falls faster than a lighter one, because it has more of that drive toward its natural place. And the thing is, in everyday life, this sort of works. It gives you roughly the right intuitions about how most objects behave most of the time. The problem is that it's wrong, and the reason the bowling ball beats the feather isn't because the bowling ball is heavier, it's because of air resistance. The feather is being slowed down by the air much more than the bowling ball is, because of its shape and surface area relative to its weight. If you removed the air, if you did the experiment in a vacuum, they'd hit the ground at exactly the same time. But Aristotle couldn't do that experiment. He couldn't create a vacuum. He didn't even believe vacuums could exist. He had philosophical arguments against the very possibility of empty space. So his theory stood, essentially unchallenged, for roughly 1,800 years. Think about that for a second. Almost 2 millennia of people accepting that heavier things fall faster. Scholars in the medieval Islamic world, thinkers in medieval Europe, generations of students who read Aristotle as if he were an authority almost equal to Scripture. It wasn't that nobody ever questioned him. There were scattered critics, particularly in the 6th century when John Philoponus in Alexandria pushed back against Aristotle's physics, arguing through thought experiments that 2 objects of different weights, dropped from the same height, would actually hit the ground at nearly the same time. And later, in the 14th century, scholars at the University of Paris, particularly Jean Buridan and Nicole Oresme, developed the concept of impetus, a kind of proto-inertia that challenged Aristotle's idea that every motion requires a continuous cause. These were real contributions, genuine intellectual progress. But none of them really overthrew the Aristotelian framework. The pieces were in place. The revolution had to wait for a man with a telescope, a bad temper, and an absolute refusal to take anyone's word for anything. Galileo Galilei, born in Pisa, Italy, in 1564. His father was a musician and music theorist, which is interesting because Vincenzo Galilei, the father, was himself something of a rebel. He'd challenged the established musical theories of his day through experiments with string tension and pitch, essentially doing empirical science in the field of music. He showed that the relationship between a string's length and its pitch could be determined through experiment, not just through the mathematical ratios that the Pythagorean tradition prescribed. So Galileo grew up in a household where authority was questioned and experiments mattered, where you didn't just accept what the old books said, you tested it. And that sensibility would define his entire career. Now, there's a famous story about Galileo and the Leaning Tower of Pisa, and you've probably heard it. The story goes that Galileo climbed to the top of the tower, dropped 2 balls of different weights, and they hit the ground at the same time, dramatically disproving Aristotle in front of a crowd of astonished onlookers. It's a great story. It's almost certainly not true, at least not in that dramatic form. The story comes from a biography written by Galileo's student Vincenzo Viviani after Galileo's death, and most historians think Viviani embellished or invented it. But here's the thing. It doesn't matter whether Galileo actually did that specific experiment, because what he did do was far more important and far more clever. What Galileo realized, probably in the 1580s and 1590s, was that dropping things straight down was actually a terrible way to study falling. Objects in free fall accelerate too quickly. At the speeds involved, with the timing instruments available in the late 16th century, which basically meant your pulse and water clocks, you just couldn't measure the motion precisely enough to learn anything useful. The whole event was over in a second or two, so Galileo did something brilliant. He slowed things down. He used inclined planes. Picture a long, smooth wooden board, tilted at a gentle angle, maybe just a few degrees off horizontal. Cut a groove down the center, as smooth as you can make it. Roll a polished bronze ball down the groove, and it accelerates, just like a falling object, but much, much more slowly. Slowly enough that you can actually measure the time it takes to cover different distances. And what Galileo found, through careful, repeated measurements, timing the ball with a water clock, weighing the water that flowed during each interval to measure the elapsed time, was a beautiful, simple pattern. The distance the ball covered was proportional to the square of the time. In the first unit of time, it covered 1 unit of distance. In 2 units of time, 4 units. In 3 units, 9. In 4 units, 16. The ball was accelerating uniformly, gaining speed at a constant rate. And he repeated the experiment more than 100 times, he tells us, and the results were consistent every time. And here's the critical discovery, the one that really overturned Aristotle. The rate of acceleration didn't depend on the weight of the ball. A heavy ball and a light ball rolled down the same incline, accelerated at the same rate. Weight didn't matter. Galileo had demonstrated that in the absence of significant resistance, all objects accelerate at the same rate under gravity. Not just roughly the same, exactly the same. He'd also distinguished between the effect of gravity itself and the effect of the medium. Air resistance was a separate thing, an impediment, not part of gravity's fundamental nature. And here's something I think about a lot, something that might stick with you as you lie there. In 1971, astronaut David Scott stood on the surface of the moon during the Apollo 15 mission and performed Galileo's experiment for real, in a genuine vacuum, with no air resistance at all. He held up a hammer in one hand and a falcon feather in the other. He let them go at the same time, and they hit the lunar surface at exactly the same instant. 330 years after Galileo published his law of falling bodies, an American astronaut on the moon confirmed it in the most dramatic way possible. The video is available, and it's wonderful to watch. You can see Scott's delight even through his visor. "How about that?" he says. Mr. Galileo was correct in his findings. That's the beauty of real physics. It doesn't just work in laboratories and textbooks. It works everywhere. On Earth, on the moon, in orbit, in the deepest reaches of space. The law is universal, and universality is perhaps the most powerful idea in all of science. Think about what that means for a moment. You, lying in your bed, are subject to the exact same gravitational laws as a star in the Andromeda galaxy, 2.5 million light-years away. The same equation that describes the force between your body and the Earth also describes the force between that star and whatever planet might be orbiting it. The same constant g, the same inverse square law, the same curvature of spacetime. Physics doesn't have separate rulebooks for different places. There's one set of rules, and everything follows them. That's not obvious. It didn't have to be that way. The universe could have been a patchwork of different physics in different regions, but it's not. And the fact that it's not, the fact that the laws are universal, is what makes science possible in the first place. If the rules changed from place to place, we couldn't learn anything about distant stars or galaxies by studying physics on Earth. But they don't change, so we can, and we do. And by the way, Galileo also figured out another beautiful thing about falling, the principle of superposition of motions. He showed that if you throw a ball horizontally off a table, the horizontal motion and the vertical fall happen independently. The ball moves forward at a constant speed while simultaneously accelerating downward. The result is a parabolic path, projectile motion, the same physics that governs a thrown baseball or a cannonball or, for that matter, a ballistic missile. He worked all of this out from his inclined plane experiments. Now, Galileo also did something else that was absolutely crucial, and it's easy to overlook because it seems so obvious to us now. He used mathematics to describe motion. Before Galileo, physics was mostly qualitative. Aristotle talked about natural motion and violent motion and tendencies toward natural places. But he didn't write equations. He didn't express physical laws as mathematical relationships. Galileo did. He said, "The distance fallen is proportional to the square of the time," and he expressed it precisely. He mathematized falling, and in doing so, he laid the foundation for everything that came after. Because once you start describing nature in mathematical terms, you can make precise predictions. You can test those predictions. You can be precisely right or precisely wrong, and that precision is what makes real science possible. Galileo published much of this work in his 1638 book, Discourses and Mathematical Demonstrations Relating to Two New Sciences, written while he was under house arrest by the Inquisition for his support of the Copernican model of the solar system. Think about that. One of the most important physics books ever written, composed by a 74-year-old man who was essentially a prisoner, going blind, smuggling his manuscript to a publisher in the Netherlands because he couldn't publish in Italy. The book covers two new sciences, the strength of materials and the motion of objects, and the ideas in it, particularly the law of falling bodies, the principle of inertia, and the analysis of projectile motion, are the seedbed from which Isaac Newton's revolution would grow just a few decades later. And there's something else Galileo gave us that's worth mentioning, because it sets up one of the most beautiful parts of the story. Galileo was the first person to turn a telescope toward the sky in 1609 and 1610, and what he saw changed everything. He saw that the moon had mountains and craters. It wasn't a perfect celestial sphere, as Aristotle had insisted. He saw that Jupiter had moons of its own, orbiting Jupiter the way our moon orbits Earth, proof that not everything in the heavens revolved around the Earth. He saw that Venus went through phases like our moon, which only made sense if Venus was orbiting the Sun, not the Earth. Each of these observations was a nail in the coffin of the old Aristotelian cosmos, the geocentric universe with the Earth at the center and the heavens made of perfect, unchanging material. The universe was a much bigger, more complex, more dynamic place than anyone had imagined. And the rules that governed it, as Galileo was beginning to show, were mathematical. But Galileo wasn't the only one doing revolutionary work on the heavens. While Galileo was rolling balls down inclined planes and peering through telescopes in Italy, a German mathematician named Johannes Kepler was doing something equally extraordinary in Prague. Kepler had gotten his hands on the most precise astronomical observations in the world, the life's work of the Danish astronomer Tycho Brahe, who had spent decades measuring the positions of the planets with a precision never before achieved, using enormous instruments on his island observatory of Uraniborg. Tycho died in 1601, and Kepler, who had been his assistant, inherited the data. And here's where Kepler's story becomes a story about perseverance, bordering on obsession. Kepler spent years, trying to fit the orbit of Mars to a circle. The ancient and medieval model of the heavens used circles, or combinations of circles, to describe planetary motion. But no matter what Kepler tried, no matter how he adjusted the circles, he couldn't get the orbit of Mars to match Tycho's observations to better than about 8 arc minutes. 8 arc minutes, that's about a quarter of the apparent diameter of the full moon. Not much. Most astronomers would have declared victory and moved on. But Kepler knew how good Tycho's data was, and he refused to accept a discrepancy of 8 arc minutes. Since divine goodness has given us a most diligent observer in Tycho Brahe, he wrote, these 8 minutes cannot be ignored. And so he kept going, and after an enormous amount of calculation, done by hand, remember, no computers, no calculators, he found the answer. The orbit of Mars wasn't a circle, it was an ellipse, a slightly squashed circle, with the sun not at the center, but at one focus of the ellipse. And this wasn't just true for Mars. It was true for all the planets. Kepler published his first 2 laws of planetary motion in 1609. Planets move in ellipses, and they sweep out equal areas in equal times, meaning they move faster when closer to the sun and slower when farther away. His 3rd law, published in 1619, related the orbital period to the average distance from the sun. These 3 laws were an extraordinary achievement, precise mathematical descriptions of how the planets actually move, but Kepler couldn't explain why. He could describe the pattern, but he couldn't identify the cause. The cause was gravity, and figuring that out would be Newton's triumph. And this is where the story starts to accelerate, if you'll forgive the pun, because what happened next was one of the great intellectual leaps in human history. Trust your dreams for the future. And it happened in a small village in Lincolnshire, England, during a plague year. And it happened inside the mind of a man who was, by all accounts, one of the strangest, most brilliant, most difficult human beings who ever lived. Isaac Newton was born on Christmas Day, 1642, in Woolsthorpe Manor, a modest farmhouse in the English countryside. His father, also named Isaac, had died 3 months before he was born. His mother remarried when Newton was 3 and essentially abandoned him, leaving him with his grandmother while she went to live with her new husband in a nearby village. Newton apparently never forgave her for this. He was by all accounts a lonely, intense, suspicious child who grew into a lonely, intense, suspicious adult. He had almost no close personal relationships throughout his life. He was secretive about his work, ferociously competitive, and capable of holding grudges for decades. He once wrote a list of his sins. This was during a period of intense religious self-examination, and among them was threatening to burn down his mother and stepfather's house with them inside it. He was also, for many years, deeply interested in alchemy and biblical chronology, spending as much time trying to decode prophecies and transmute metals as he did on the physics we remember him for. He was not a warm person. He was not an easy person. But he was, beyond any reasonable argument, one of the 2 or 3 greatest scientific minds in human history, and the story of how he came to his theory of gravity is one of the most celebrated tales in all of science, even though, like the Galileo Tower story, the popular version is a bit simplified. Here's what actually happened. In 1665, when Newton was 22 years old and a student at Trinity College, Cambridge, the university closed because of the Great Plague. The bubonic plague was sweeping through England. It would kill roughly 1/4 of London's population, and Cambridge sent its students home. Newton went back to Woolsthorpe, to the family farmhouse, and he stayed there for roughly 18 months. And during that period, which historians call Newton's annus mirabilis, his miracle year, though it was actually closer to a year and a half, he did work that would reshape human understanding of the universe. He developed calculus, though he called it the method of fluxions. He did groundbreaking work on optics, showing that white light is composed of a spectrum of colors by passing it through a prism, and he began thinking about gravity. Now, the apple story. Did an apple really fall on Newton's head? Almost certainly not on his head. But Newton himself, late in life, told the story to several people, including his friend William Stukeley, who recorded it in 1726. Newton said that while sitting in the garden at Woolsthorpe, he saw an apple fall from a tree, and it set him wondering. The apple fell straight down. It didn't go sideways. It didn't fall upward. It went toward the center of the earth. And it didn't matter how high the tree was, the apple would still fall. What if the force that pulled the apple down extended much farther than anyone had imagined. What if it reached beyond the treetop, beyond the hilltops, beyond the clouds? What if it reached all the way to the moon? This was the key insight, and it's genuinely revolutionary. So let's slow down and really appreciate it. Before Newton, people thought of earthly gravity and the motion of celestial bodies as completely separate things. Down here on Earth, things fell. Up there in the heavens, planets orbited in circles or ellipses, following mathematical rules that Johannes Kepler had worked out in the early 1600s from the painstaking observations of Tycho Brahe. Kepler's 3 laws of planetary motion described the shapes and timing of orbits with remarkable precision. He showed that planets move in ellipses with the sun at one focus, that they sweep out equal areas in equal times, and that the square of a planet's orbital period is proportional to the cube of its average distance from the sun. Beautiful mathematical patterns. But Kepler didn't know why the planets moved that way. He guessed it was some kind of magnetic influence from the sun, a sweeping force that pushed the planets along, but he couldn't pin it down. The motion of the planets and the fall of an apple were, as far as anyone knew, unrelated phenomena. Newton's genius was to ask, what if they're the same thing? What if the force that pulls the apple to the ground is the same force that keeps the moon in orbit around the Earth and the planets in orbit around the sun? What if gravity isn't just a local, earthly phenomenon, but a universal force? Every object with mass attracting every other object with mass, everywhere in the universe. That word, universal, is doing enormous work here. Think about how bold a claim this is. Newton is saying that the same law, the same equation, the same fundamental force governs the apple falling from the tree, the moon orbiting the Earth orbiting the sun, the moons of Jupiter, the tides of the ocean, all of it. One law for everything. That's not a small claim. That's arguably the most ambitious claim in the history of science up to that point. And he tested it, even in those early months at Woolsthorpe. He asked, if the force of gravity reaches to the moon, and if it weakens with the square of the distance, an idea he likely got from thinking about how light spreads out from a point source, then does the moon's orbital motion match what you'd predict? The moon is about 60 Earth radii away from the center of the Earth. If gravity falls off as the square of the distance, then the gravitational acceleration at the moon's distance should be about 1/3600th of the acceleration at the Earth's surface. And you can check that against the moon's actual orbital motion, how fast it needs to be falling toward the Earth to maintain its circular orbit. When Newton did this calculation, using the best values available, the numbers roughly agreed. Not perfectly. The value he had for the Earth's radius was a bit off, but close enough to be very encouraging, close enough to suggest he was onto something enormous. He didn't publish any of this. He tucked it away and went back to Cambridge when the plague subsided. Now, Newton didn't publish his theory of gravity for over 20 years. The initial thinking happened during the plague years of 1665 and 1666, but the full theory wasn't presented to the world until 1687, when Newton published his masterwork, Philosophiae Naturalis Principia Mathematica, the mathematical principles of natural philosophy, usually just called the Principia. And the story of how the Principia came to be written is itself a wonderful tale of rivalry, flattery, and one man's incredibly fortunate timing. By the early 1680s, several people were circling around the idea of a gravitational force that weakened with distance. Robert Hooke, the brilliant and contentious curator of experiments at the Royal Society, a man who invented or improved countless instruments, discovered cells, and feuded with nearly everyone, had proposed that gravity followed an inverse square law. If you double the distance, the force drops to a quarter. Triple the distance, it drops to a ninth. Hooke had the right idea, but he couldn't prove it. He couldn't show mathematically that an inverse square force would produce the elliptical orbits that Kepler had observed. Christopher Wren, the famous architect, offered a prize to anyone who could provide the proof. Edmund Halley, yes, the one the comet is named after, also suspected the inverse square law was correct, and in August of 1684, he traveled to Cambridge to ask Newton about it. The conversation, reconstructed from later accounts, went something like this. Halley asked Newton what shape of orbit a planet would follow under an inverse square gravitational force. Newton answered immediately, an ellipse. He'd worked it out years earlier, during the plague years. Halley, astonished, asked to see the proof. Newton rummaged through his papers, couldn't find it, but promised to redo the calculation and send it along. And he did more than that, way more. What started as a 9-page paper called De Motu Corporum in Gyrum, on the motion of bodies in orbit, turned into the Principia, nearly 500 pages of the most concentrated brilliance in the history of science. Newton essentially laid out the entire framework of classical mechanics, his 3 laws of motion, his law of universal gravitation, his mathematical tools for solving problems involving forces and motion, and then used it to explain the motion of the planets, the comets, the moon, the tides, the precession of the equinoxes, the shape of the Earth, the trajectories of projectiles, and more. All from a handful of basic principles. Halley, who recognized what he was looking at, personally financed the publication of the book after the Royal Society ran out of money, having spent its budget on a lavish illustrated history of fish. That's a real fact, by the way. The Principia, arguably the most important scientific book ever written, almost wasn't published because the Royal Society blew its budget on a book about fish. Halley paid out of his own pocket. Science owes him a considerable debt. So what exactly did Newton's law of gravity say? Let's lay it out clearly, because it's beautiful in its simplicity. Every object with mass attracts every other object with mass. The force of attraction between any 2 objects is proportional to the product of their masses, and inversely proportional to the square of the distance between their centers. More mass means more pull. More distance means less pull, and it drops off fast. That square is important. If you move twice as far away from something, the gravitational pull doesn't just halve, it drops to a quarter. Move 10 times as far, and it drops to 1/100th. It weakens rapidly with distance, but it never, ever reaches 0. In principle, every object in the universe is gravitationally pulling on every other object, right now, no matter how far apart they are. The gravitational pull between you and a star in the Andromeda galaxy is unimaginably small, but it's not 0. It exists. There's a number in Newton's equation, a constant, that sets the overall strength of gravity. It's called the gravitational constant, and we usually write it as capital G. Newton didn't know its actual value. He knew the law, the shape of the equation, but not the specific number that would let you plug in masses in kilograms and distances in meters and get a force in newtons. Figuring out that number, actually measuring how strong gravity is, would have to wait for another century and one of the most delicate experiments ever performed. But we'll get there. First, let's just sit with what Newton had achieved, because it really is breathtaking. He'd unified terrestrial and celestial physics. He'd shown that the same force that makes an apple fall makes the moon orbit. He'd explained Kepler's laws of planetary motion, all 3 of them, as natural consequences of a simple inverse square force law, the elliptical orbits, the equal area law, the relationship between orbital period and distance. All of it just fell out of Newton's equations. He'd explained the tides as a result of the moon's and sun's gravitational pull on the Earth's oceans. He'd calculated the shape of the Earth, slightly bulging at the equator, because its rotation flings material outward while gravity pulls it in, an oblate spheroid rather than a perfect sphere. He'd predicted the paths of comets, showing that Halley's comet, for instance, followed a highly elongated elliptical orbit and would return periodically. All of this from one equation, and the equation worked. It didn't just qualitatively explain things. It made precise, quantitative predictions that could be, and were, verified by observation. There's one more thing about Newton's gravity that's worth savoring before we move on, and it has to do with something Newton himself didn't fully appreciate: the profound universality of what he'd done. Before Newton, people assumed that the heavens were fundamentally different from the Earth. Different matter, different rules, different physics. The sublunary world, everything below the moon, was imperfect, changeable, subject to decay. The superlunary world, the heavens, was perfect, eternal, made of a special fifth element, the quintessence. This division goes back to Aristotle, and it persisted for nearly 2,000 years. The heavens were divine territory. Earth was Earth, and to suggest that the same grubby, ordinary physics that governed falling rocks and flowing water also governed the motion of the planets, that was, in its time, almost as revolutionary as the heliocentric model itself. Newton demolished that wall. He showed that there is no wall. The same force, described by the same equation, governs the fall of an apple and the orbit of Jupiter. The heavens are not special. They're not made of different stuff. They follow the same laws as everything else. And that insight, that the laws of physics are the same everywhere, that the universe is fundamentally uniform in its basic principles, became one of the foundational assumptions of all modern science. We take it for granted now, but it was earned, hard-won, and it started with Newton asking whether the moon is falling. And one more thing about Newton, because his legacy is so central to this whole story. Newton lived until 1727. He was 84 years old, which was extraordinary for the time, and he spent the second half of his life not doing physics. After the Principia, he became increasingly involved in other pursuits. But he was appointed Warden of the Royal Mint in 1696, and then Master of the Mint in 1699, and he threw himself into the job with characteristic intensity, personally pursuing counterfeiters and overseeing the great recoinage of England's silver currency. He served as president of the Royal Society for over 2 decades, ruling it with an iron hand. He was knighted in 1705, and he spent enormous amounts of time on alchemy and biblical chronology, neither of which produced results that we remember today. But the physics he did in his 20s and 30s, the calculus, the optics, the laws of motion, the universal law of gravitation, that changed the world forever. For over 2 centuries after the Principia, Newtonian mechanics was physics. It was the framework within which everything else was understood. And even today, after Einstein, after quantum mechanics, Newton's equations remain the workhorses of engineering, of space exploration, of every bridge and building and satellite in the world. They work. They're an approximation of something deeper, but in the domain of everyday experience, they're so close to exact that the difference is unmeasurable. But here's the thing, and this is important for our story tonight. Newton's theory of gravity had a feature that deeply bothered Newton himself, and it bothered other physicists for 2 centuries, and it turned out to be a genuine clue that something deeper was going on. The problem was action at a distance. Think about what Newton's law actually says. The Earth pulls on the moon, right now, across almost 240,000 miles of empty space. How? Through what mechanism? What reaches across that void and tugs on the moon? Newton's equation tells you how strong the pull is, and how it depends on mass and distance, but it says nothing about how the force gets from here to there. It's instantaneous, according to the math. If the sun suddenly disappeared, just vanished, Newton's law implies that the Earth would instantly feel the loss of the sun's gravity and fly off in a straight line. No delay, no signal traveling across space. Just instant, spooky action at a distance. Newton hated this. He wrote about it explicitly. In a letter to Richard Bentley in 1693, he said, and I'm paraphrasing, but the sentiment is exact, that the idea that one body could act on another through a vacuum, without any intermediary, at any distance, was to him so great an absurdity that he believed no person who had a competent faculty of thinking could ever fall into it. He was saying, I know my theory has this feature, and I find it philosophically repulsive, but the math works, and I can't explain the mechanism. In the Principia itself, he wrote the famous phrase, hypotheses non fingo. I frame no hypotheses, meaning, I'm not going to speculate about how gravity transmits its influence. The equation works. I'll leave the mechanism for someone else to figure out. And the criticism wasn't just philosophical. The great German mathematician and philosopher Gottfried Wilhelm Leibniz, who had independently invented calculus and was engaged in a bitter priority dispute with Newton over that very claim, attacked action at a distance as a return to occult qualities, a stinging accusation in an era when science was trying to distance itself from mysticism and alchemy. Leibniz wanted a mechanical explanation, gears and pushes and physical contact, and Newton couldn't provide one. The French philosopher Voltaire, who did more than anyone to popularize Newton's ideas on the continent, acknowledged the strangeness, but argued that the predictive power of the theory outweighed the philosophical discomfort. We should like to know what gravity is, Voltaire wrote. If we ever discover, we shall only know one link more of an infinite chain. And that's exactly what happened, though it took more than 200 years and required a complete reimagining of space and time itself. But before we get to Einstein and that reimagining, there's a lot of story to tell, because Newton's theory wasn't just a theoretical triumph. It became the most powerful practical tool in all of science, and the things people did with it in the 18th and 19th centuries are some of the most beautiful achievements in the history of human thought. Let's start with a problem that sounds almost absurd when you first hear it. How much does the Earth weigh? Not how much does something weigh on the Earth, how much does the Earth itself weigh? You can't exactly put it on a scale, but Newton's law of gravity gives you a way to approach the question. If you can measure one crucial number, the gravitational constant g. Here's the logic. We know the acceleration due to gravity at the Earth's surface. It's about 9.8 meters per second squared. Galileo essentially figured that out with his inclined planes. And Newton's law tells us that this acceleration equals g times the mass of the Earth divided by the square of the Earth's radius. We can measure the Earth's radius. Eratosthenes roughly did that back in ancient Egypt, around 240 BCE, by comparing shadow lengths in two cities, and by the 18th century, it was known with pretty good accuracy. So if you know g, you can solve for the mass of the Earth. But measuring g requires measuring the gravitational attraction between two known masses in a laboratory, and that force is incredibly tiny. Gravity is absurdly weak compared to the other forces of nature. Pick up a refrigerator magnet. That little magnet, with its tiny electromagnetic force, is overpowering the gravitational pull of the entire Earth on the bit of metal it's sticking to. The electromagnetic force between two protons is roughly 1,000 trillion times stronger than the gravitational force between them. That's 10 to the 36th power. To measure gravity between laboratory-sized objects, you need an experiment of extraordinary delicacy. And that experiment was done in 1798 by one of the most eccentric and reclusive scientists in history, Henry Cavendish. Born in 1731 in Nice, France, his mother was there for the warm climate during her pregnancy, into one of the wealthiest aristocratic families in England. His grandfather was the Duke of Devonshire. Cavendish inherited an enormous fortune and essentially ignored it, living simply and spending almost all of his time in his private laboratory. He was, by all accounts, almost pathologically shy. He could barely speak to people, especially women. He communicated with his household servants by written notes. He had a separate staircase built in his house so he wouldn't have to encounter the female staff. He attended meetings of the Royal Society regularly, but would stand in the hallway unable to enter if there were too many people inside. If someone approached him at a meeting and spoke to him, he would often emit a high-pitched squeak and shuffle away. He once left a dinner party through a back window to avoid having to pass by the other guests on the way out. And yet, behind that agonizing shyness was one of the most precise experimental minds the world has ever known. He did groundbreaking work in chemistry. He discovered hydrogen, which he called inflammable air, and in electricity, anticipating several of the discoveries later attributed to Coulomb, Ohm, and Faraday, but publishing almost none of it. Cavendish's gravity experiment used a device called a torsion balance, originally designed by the geologist John Michell, who died before he could use it, and whose apparatus was eventually acquired by Cavendish. The setup was elegant. 2 small lead balls, each about 2 inches in diameter, were attached to the ends of a lightweight horizontal wooden bar, about 6 feet long. The bar was suspended from its center by a very thin wire, a torsion fiber, so it could rotate freely in the horizontal plane. Then 2 large lead balls, each about 12 inches in diameter and weighing about 350 pounds, were brought near the small ones on opposite sides. The gravitational attraction between each large ball and its neighboring small ball would cause the bar to twist, ever so slightly, twisting the torsion fiber. And by measuring how much the bar twisted, which Cavendish did by observing the deflection of a tiny beam of light reflected from a mirror attached to the wire, and knowing the torsional stiffness of the wire and the masses of all 4 balls, you could calculate the gravitational force between them, and therefore the value of g. The forces involved were incredibly tiny. The twist was minuscule. The small balls moved by only a fraction of an inch. Cavendish put the entire apparatus in a sealed wooden shed and observed it from outside through telescopes, to avoid disturbing the system with air currents from his own body heat or vibrations from his footsteps. He made measurements over many months, with extraordinary care and patience, recording the oscillation period of the bar as it swung back and forth before settling into its new equilibrium. And when he was done, he had a value for what he described as the density of the Earth. That's how he reported it, being a modest and precise man who preferred to state what he'd actually measured rather than extrapolate, from which you could immediately get the Earth's mass. The number he got was remarkably close to the modern value. The Earth's mass is about 5.97 times 10 to the 24 kilograms. That's roughly 6 trillion kilograms. Cavendish's measurement, done in a shed with lead balls and a twisted wire in 1798, was accurate to within about 1% of the value we use today. That's the kind of experimental craftsmanship that takes your breath away when you really think about it. He essentially weighed the Earth using a few hunks of lead and a piece of wire. And in doing so, he completed Newton's equation. He put a number on the constant g, and now you could calculate the gravitational force between any 2 objects in the universe, provided you knew their masses and the distance between them. Now, let me tell you about the tides. Because the tides are one of those things that seems simple on the surface, but turns out to be beautifully complicated when you actually think about the physics. And Newton was the first person to give a real explanation of why they happen. You know the basic phenomenon. The ocean rises and falls roughly twice a day, at coastlines all around the world. Sailors and fishermen have known about tides for thousands of years. Many ancient cultures associated tides with the moon, which was observationally correct. The tides are indeed correlated with the moon's position, but the mechanism was mysterious. How does the moon, 250,000 miles away, push and pull the oceans? Newton's answer was gravitational, and it's subtle. The moon's gravity pulls on the Earth, but it pulls more strongly on the side of the Earth closest to the moon than on the side farthest away, because gravitational force decreases with distance. This difference in gravitational pull, the tidal force, stretches the Earth slightly along the Earth-Moon line. The ocean, being fluid, responds to this stretching more visibly than the solid Earth does, creating a bulge of water on the side of the Earth facing the moon. And here's the part that surprises most people. There's also a bulge on the opposite side of the Earth, the side farthest from the moon. That's because the far side of the Earth feels the moon's pull less strongly than the center does. So relative to the center of the Earth, the water on the far side gets left behind, creating a second bulge. As the Earth rotates beneath these two bulges, any given coastline passes through 2 high tides and 2 low tides roughly every 24 hours and 50 minutes. The extra 50 minutes comes from the fact that the moon is also orbiting the Earth, so the Earth has to rotate a bit extra each day to catch up. The actual pattern of tides at any specific location is enormously complicated. The shapes of ocean basins, the depth of the water, the contours of the coastline, resonance effects, all of these modify the simple two-bulge picture. Some places get just 1 high tide per day. Some get tides that are enormous. The Bay of Fundy in Canada has tidal ranges of up to 16 meters, about 50 feet, while other places have tides of only a few centimeters. And the sun also contributes its own tidal force, about half as strong as the moon's, despite being vastly more massive, because tidal force depends on the difference in gravity across the width of the Earth, and the sun is so much farther away that the percentage change is smaller. Spring tides, the especially high tides that occur when the sun and moon are aligned, happen because the sun's tidal effect reinforces the moon's. Neap tides, the weaker tides when the sun and moon are at right angles, happen because they partially cancel each other out. The point is, Newton's law of gravity explained all of this. Not just qualitatively, not just the moon pulls on the water, but quantitatively. And that practical power, that ability to make precise predictions you could check against reality, is what made Newtonian gravity so compelling. And the triumph wasn't just in predicting planets. The 18th century saw Newtonian gravity applied to an astonishing range of problems. Pierre-Simon Laplace, the French mathematician who is sometimes called the French Newton, wrote a massive 5-volume work called Mécanique Céleste, Celestial Mechanics, published between 1799 and 1825, in which he worked out the gravitational interactions among all the planets with extraordinary detail. He showed that the solar system was stable, that the planets' mutual gravitational tugs, while causing orbits to wobble and precess, didn't build up over time to catastrophic instability. The solar system would hold together. When supposedly asked Laplace why God didn't appear in his system, Laplace replied, "I had no need of that hypothesis." Whether the story is exactly true is debated, but it captures the spirit of the era. Newtonian gravity was so powerful, so complete, so capable of explaining the heavens, that there seemed to be no room left for mystery. Leonhard Euler, the most prolific mathematician in history, applied Newton's laws to the motion of the moon with extraordinary precision, producing lunar tables that were used for navigation. Getting the moon's motion right was one of the hardest problems in celestial mechanics. The moon is pulled by both the Earth and the Sun, and the resulting three-body problem has no exact analytical solution. Euler, along with Alexis Clairaut and Jean-Laurent d'Alembert, developed approximation methods that gradually tamed the problem. And their solutions had real-world consequences. Accurate lunar tables meant more accurate navigation at sea, which meant fewer shipwrecks, which meant more trade, more exploration, more connection between distant parts of the world. Gravity, abstract and mathematical, was saving lives and shaping economies. Even the shape of the Earth was a triumph of Newtonian gravity. Newton predicted that the Earth should be slightly flattened at the poles and bulging at the equator because its rotation flings material outward at the equator while gravity pulls it in. This oblate shape was controversial. The French astronomer Jacques Cassini claimed his measurements showed the opposite, that the Earth was elongated at the poles like a lemon rather than flattened like a tangerine. In the 1730s, the French Academy of Sciences sent 2 expeditions to settle the question. One to Lapland in the Arctic, led by Pierre-Louis Maupertuis, and one to Peru, near the equator, led by Charles-Marie de la Condamine. After years of painstaking surveying in extreme conditions, mosquitoes, altitude sickness, political intrigue, the results came in. Newton was right. The Earth was flattened. 1 degree of latitude was longer near the poles than near the equator, exactly as Newton's theory of gravity predicted. The universal law held, even for the shape of the world beneath your feet. But the most dramatic triumph of Newtonian gravity, the one that really cemented its status as the most successful theory in science, was the discovery of Neptune. And this story is so good, so beautifully dramatic, that it's worth slowing down and giving it the space it deserves. By the early 19th century, astronomers had mapped the orbit of every known planet with remarkable precision, using Newton's laws to predict where each planet should be at any given time. And the predictions were astonishingly accurate. Mercury, Venus, Mars, Jupiter, Saturn, all of them followed their predicted paths beautifully. The solar system was a clockwork, and Newton's law was the mechanism that made it tick. But Uranus, discovered by William Herschel in 1781, actually discovered by accident while Herschel was conducting a systematic survey of the sky from his garden in Bath, England, Uranus was misbehaving. Uranus wasn't quite where it was supposed to be. Astronomers would calculate its orbit using Newton's laws, carefully accounting for the gravitational tugs of Jupiter and Saturn, and the prediction would be slightly off, not by much, a tiny angular discrepancy on the sky, but it was persistent and it was growing. By the 1840s, the discrepancy was large enough that it couldn't be dismissed as observational error. Something was pulling on Uranus, something that wasn't in the calculations. 2 mathematicians, working independently and unaware of each other, took on the challenge. One was John Couch Adams, a young Englishman at Cambridge, quiet and methodical. The other was Urbain Le Verrier, a Frenchman, working at the Paris Observatory, brilliant and imperious. Both of them did the same thing. They assumed Newton's law was correct. They assumed there was an unseen planet, and they worked backward from the observed deviations of Uranus to calculate the mass, distance, and position of the unknown body. This is an incredibly difficult mathematical problem. You're essentially solving Newton's equations in reverse, with multiple unknowns, using the tiny wobbles of one planet's orbit as your only data. It's like listening to the echo of a voice in a canyon and trying to calculate the shape of the walls. Adams finished his calculations first, in September of 1845, and sent his predictions to James Challis, the director of the Cambridge Observatory, and to George Airy, the Astronomer Royal at Greenwich. Neither of them acted on it with any urgency. Airy sent Adams a follow-up question about a technical detail, and when Adams didn't reply quickly enough, he was shy and bad at correspondence, Airy set the matter aside. Leverrier completed his calculations independently in the summer of 1846. He also had trouble getting French astronomers to search for the planet. There's a whole tangled political backstory about observatory priorities, so he sent his predicted position to Johann Galle at the Berlin Observatory on September 23, 1846. Galle received the letter on the 23rd, and that same evening, he and his assistant Heinrich d'Arrest pointed their telescope at the spot Leverrier indicated. They found Neptune within 1 degree of the predicted position on their very first night of looking. The discovery of Neptune was an absolute sensation. It was the most spectacular confirmation of Newton's law of gravity imaginable. A planet discovered not by looking through a telescope, but by doing mathematics on a piece of paper. The gravitational equations had predicted the existence and location of a world that no human eye had ever seen. If anyone had lingering doubts about whether Newton's law was truly universal, Neptune put them to rest. Gravity worked. The math worked. The universe obeyed the equations. There was an ugly priority dispute between England and France about who deserved credit, Adams or Leverrier, and the nationalistic feelings ran high, as you can imagine. Today, both men are credited. But here's the thing about spectacular successes. They can make it very hard to notice when something is slightly wrong. And something was slightly wrong. There was another planet, the innermost planet, that was also misbehaving. And this time, no hidden planet could fix the problem. And that tiny, stubborn discrepancy, ignored and explained away for decades, would eventually crack open Newton's entire framework and lead to the most profound reimagining of space, time, and gravity in the history of physics. The planet was Mercury, and the problem was with the point in its orbit where it passes closest to the Sun, a point called the perihelion. Mercury's orbit is an ellipse, and because of gravitational tugs from the other planets, that ellipse slowly rotates over time. The long axis of the oval gradually swivels around, a phenomenon called the precession of the perihelion. Newtonian physics could account for most of this precession. The gravitational influence of Venus accounts for most of it, with Jupiter, Earth, and the other planets contributing smaller amounts. But when you added it all up, you came short. The observed precession was slightly larger than what Newton's theory predicted. The discrepancy was about 43 arcseconds per century, where an arcsecond is 1/3600th of a degree. That's an incredibly small angle. You'd never notice it with the naked eye. But it was there. It was persistent, and nobody could make it go away. Leverrier, riding high on his Neptune triumph, naturally proposed the same solution. There must be another planet, even closer to the Sun than Mercury, whose gravity was causing the extra precession. He even gave it a name, Vulcan, and for decades, people searched for it. There were scattered reports of a dark body crossing the face of the Sun, amateur astronomers claiming sightings, brief periods of excitement followed by failure to replicate. But Vulcan was never confirmed. It didn't exist. No new planet was going to save Newton's theory this time. For decades, this remained a minor puzzle. Annoying, but not alarming. The discrepancy was so small that most physicists assumed it would eventually be explained within the Newtonian framework. Some refinement of the calculations, some overlooked perturbation, some subtle effect of the sun's shape. It wasn't the kind of thing that makes you question the foundations of physics. And that's the tricky thing about paradigm shifts. The cracks that eventually bring down a theory almost never look like cracks at the time. They look like minor bookkeeping problems, loose ends that somebody will tie up sooner or later. But sometimes, those loose ends are attached to something enormous. And the person who pulled on that particular loose end, who followed it all the way down and discovered that it was connected to the very fabric of reality itself, was, of course, Albert Einstein. And the story of how Einstein reinvented gravity is one of the most extraordinary intellectual journeys in human history. It took him 10 years, from 1905 to 1915, and it nearly broke him. He described it as the hardest thing he ever did, the most difficult intellectual labor of his life. And given that this is the same person who revolutionized physics with special relativity, explained the photoelectric effect, and essentially proved the existence of atoms, that's saying something. But before we can get to what Einstein built, we need to understand what he started with, and the trail that led him to rethink everything Newton had laid down begins with a deceptively simple question, a question so obvious that most people don't even think to ask it, and yet it contains the seed of a completely new theory of gravity. The question is this: why does everything fall at the same rate? Remember, Galileo showed that all objects, regardless of their mass, accelerate at the same rate under gravity. Newton's law explains this, sort of. The gravitational force on an object is proportional to its mass, but so is the resistance of the object to acceleration. That's Newton's second law. Force equals mass times acceleration. The mass appears on both sides of the equation and cancels out, leaving you with an acceleration that depends only on the mass of the Earth and your distance from its center, not on your own mass. Heavy things feel more pull, but they're also harder to accelerate, and the two effects exactly cancel. But here's what's weird about that. The mass that appears in the gravitational force law, let's call it gravitational mass, the mass that determines how strongly gravity pulls on you, has no obvious reason to be exactly equal to the mass that appears in Newton's second law. Let's call that inertial mass, the mass that determines how much you resist acceleration. Gravitational mass is about how much gravity affects you. Inertial mass is about how hard you are to push. They're conceptually completely different things. It's as if your susceptibility to a force and your resistance to all forces just happened, by cosmic coincidence, to be described by the exact same number. Newton noticed this and tested it. He did pendulum experiments showing that the period of a pendulum doesn't depend on the mass or material of the bob, which confirms the equality. But he couldn't explain it. He just accepted it as an empirical fact, a coincidence. An incredibly precise coincidence, because experiments have since confirmed the equality of gravitational and inertial mass to about 1 part in 100 trillion. Baron Lorand Eötvös in Hungary did beautiful torsion balance experiments around 1900, establishing this to extraordinary precision, and modern experiments have pushed even further. Einstein didn't think it was a coincidence, and his insight, the one he later called the happiest thought of my life, came in 1907, 2 years after he published Special Relativity. He was sitting in the patent office in Bern. He was still at the patent office, still third-class technical expert, and he imagined a person falling freely. A person who had just stepped off a roof, and he realized that a person in free fall doesn't feel gravity. If you're falling freely, not through air with wind resistance, but truly freely, in a vacuum, you feel weightless. You and everything around you are accelerating at exactly the same rate, so relative to your immediate surroundings, Nothing is happening. You're floating. An astronaut in orbit is in exactly this situation. They're falling freely around the Earth, in constant free fall, and they experience weightlessness. They're not beyond the reach of Earth's gravity. Gravity at the altitude of the International Space Station is still about 90% as strong as on the surface. They float because they're falling, continuously, and the station is falling with them. And here's Einstein's leap. If a person in free fall can't tell the difference between floating in zero gravity and falling in a gravitational field, then maybe gravity and acceleration are, in some deep sense, the same thing. This is the equivalence principle, and it's the foundation of everything that follows. Let me make this concrete. Imagine you're in a closed box, like an elevator, with no windows. You feel your feet pressing on the floor. You feel your normal weight. Now, are you standing on the surface of the Earth, with gravity pulling you down? Or are you in deep space, far from any planet or star, and the elevator is accelerating upward at 9.8 meters per second squared, pushing the floor into your feet? The equivalence principle says there is no experiment you can do inside that box that will tell you which scenario is true. Gravity pulling you down and the floor accelerating up into you feel exactly the same. They're physically indistinguishable. Drop a ball, it falls the same way. Pour a glass of water, it pours the same way. Stand on a bathroom scale, it reads the same number. Now, if you're thinking, okay, that's kind of interesting, but so what? Here's where it gets really profound. Because Einstein realized that if gravity and acceleration are equivalent, then anything that happens in an accelerating reference frame must also happen in a gravitational field. And one of the things that happens in an accelerating frame is that light bends. Picture this. You're in that accelerating elevator in deep space. A beam of light enters through a small hole in one wall, traveling horizontally. In the time it takes the light to cross the elevator has accelerated upward slightly, which means the floor has moved up a tiny bit, which means the light hits the opposite wall at a point slightly lower than where it entered. From inside the elevator, the light appears to curve downward, and if acceleration and gravity are truly equivalent, then light must also bend in a gravitational field. Gravity bends light. Another thing Einstein figured out from the equivalence principle: gravity affects time. Imagine that accelerating elevator again, but now think about a clock at the floor and a clock at the ceiling. The floor is accelerating toward each pulse of light sent down from the ceiling clock, so the floor clock receives those pulses at a higher rate. They're blue-shifted. Conversely, the ceiling is accelerating away from pulses sent up from the floor clock, so it receives those pulses at a lower rate. They're red-shifted. The floor clock, from the perspective of the ceiling clock, appears to tick more slowly, and by the equivalence principle, the same thing happens in a gravitational field. Clocks in stronger gravity tick more slowly. Time itself runs slower, closer to a massive body. These were testable predictions, and they were predictions that Newton's theory couldn't make. This was new territory. But Einstein, in 1907, had the equivalence principle and a few startling consequences. He didn't yet have a complete theory. That would take 8 more years of struggle, and the struggle was brutal. Here's the thing about the equivalence principle. It tells you that gravity and acceleration are locally the same. In a small region, for a short time, they're indistinguishable. But globally, they're not. A real gravitational field, like the Earth's, has tidal effects. It's stronger, closer to the Earth, and weaker farther away. And it points in different directions at different locations because it always points toward the center. An accelerating elevator doesn't have these features. So the equivalence principle is a local statement, not a global one. And Einstein needed a global theory. A theory that described gravity, not just at one point, but everywhere. A theory that could handle the complex, varying gravitational fields of planets, stars, and galaxies. And here's where Einstein had what might be his deepest insight, the one that took the longest to develop and required the most painful mathematical learning. He realized that what we experience as gravity is not a force at all. It's geometry. The presence of mass and energy warps the geometry of space and time, and what we perceive as gravitational attraction is actually objects following the straightest possible paths through this warped geometry. Let me try to make this intuitive, because it's one of those ideas that sounds insane the first time you hear it, but is actually beautiful once it clicks. Think about what it means to travel in a straight line on a curved surface. If you're walking on a flat field and you go straight forward, you trace a straight line. Simple. But if you're walking on the surface of a sphere, the Earth, say, and you walk straight forward, never turning left or right, you trace out what's called a great circle. That's the straightest possible line on a curved surface. Airlines follow great circle routes because they're the shortest paths between 2 points on a globe, even though on a flat map those routes look curved. Einstein's insight was that mass and energy curve space and time in a similar way, and objects moving through that curved spacetime follow the straightest possible paths, what mathematicians call geodesics. The Earth doesn't orbit the Sun because some invisible force is pulling it. It orbits because the Sun's mass has warped the spacetime around it, and the Earth is simply following the straightest possible path through that warped geometry. It only looks like the Earth is being deflected from a straight line because we're thinking in terms of flat Newtonian space. In the actual geometry of spacetime, which is curved by the Sun's mass, the Earth's orbit is a geodesic. It's the natural, unforced path. The same goes for you. Right now, you feel gravity pulling you into the bed. In Newtonian terms, the Earth's mass is exerting a force on you. But in Einstein's picture, the Earth's mass has curved the spacetime around it, and the natural geodesic path for you would be to fall freely, to accelerate toward the center of the Earth. The bed is preventing you from following that geodesic. The force you feel, the weight pressing you into the mattress, isn't gravity pulling you down. It's the bed pushing you up, preventing you from following the natural curved path of spacetime. Gravity, in Einstein's picture, isn't a force at all. It's the shape of the world. This is genuinely one of the most profound reconceptualizations in the history of thought. And translating this beautiful geometric insight into actual mathematics was the hardest part, and it nearly defeated Einstein. He needed a mathematical framework that could describe the curvature of four-dimensional spacetime in a way that was consistent with the equivalence principle and reduced to Newton's theory in the appropriate limit. And the mathematics he needed had been developed by Bernhard Riemann in the 1850s and further refined into what's called tensor calculus, or Riemannian geometry. Einstein enlisted the help of his friend Marcel Grossmann, a mathematician at the ETH in Zurich, who introduced him to the tools. Let me give you a sense of just how difficult Einstein's journey was between 1912 and 1915, because it's one of the great intellectual dramas in the history of science. In 1912, Einstein moved from Prague to Zurich to take a position at the ETH, and it was there that Grossmann introduced him to Riemannian geometry. Einstein later said that compared to the problem of general relativity, special relativity had been child's play. The math was ferocious. He was working with tensors, mathematical objects that generalize vectors and matrices to higher dimensions, and the notation alone was enough to give most physicists headaches. He filled notebooks with calculations, many of which led nowhere. He and Grossman published a preliminary theory in 1913 called the Entwurf theory, outline theory, that looked promising but turned out to be wrong. The equations weren't generally covariant, meaning they took different forms in different coordinate systems, and Einstein spent much of 1913 and 1914 convinced that this was actually a feature, not a bug. He even published arguments claiming to prove that generally covariant field equations were impossible. He was wrong about that, and realizing his mistake was part of what led to the final breakthrough in November 1915. During this period, Einstein's personal life was also falling apart. His marriage to Mileva Maric was disintegrating. They separated in 1914 when Einstein moved to Berlin and Mileva stayed in Zurich with their 2 sons. The emotional strain was enormous. He wrote letters that veered between exhilaration over physics and despair over his family situation. He was working in Berlin during the first years of World War I, which he opposed. He was one of the few German academics who didn't sign the infamous Manifesto of the 93, supporting the German war effort. He was isolated, under stress, and grappling with the hardest mathematical problem he'd ever faced. And then, in the summer and fall of 1915, things came to a head. David Hilbert, one of the greatest pure mathematicians alive, had become interested in Einstein's problem. Hilbert invited Einstein to Göttingen to give a series of lectures in June 1915, and Einstein, perhaps unwisely, shared his entire approach, including his current difficulties. Hilbert, with his formidable mathematical machinery, began working on the problem himself. Einstein, aware that Hilbert was on his trail, worked with desperate intensity through October and November. His notebooks from this period show a man pushing himself to his absolute limit, trying idea after idea, correcting errors, backtracking, pushing forward again. The result was those 4 extraordinary November lectures to the Prussian Academy. On November 4th, he presented a new set of field equations that were generally covariant but not quite right. On November 11th, he corrected them. On November 18th, he showed that the corrected equations gave the right precession of Mercury, and that's when he knew he had it. And on November 25th, he presented the final equations in their definitive form. The general theory of relativity was complete. Einstein later said those November weeks were the most exciting and intense of his scientific life. "My boldest dreams have now come true," he wrote to a friend. And to another, "The theory is of incomparable beauty." He was right about that. It is beautiful. And the fact that it emerged from years of wrong turns, frustration, personal upheaval, and sheer stubborn refusal to give up makes it, if anything, more beautiful. The theory didn't arrive as a revelation. It was fought for, error by error, correction by correction, until finally the pieces locked into place. And in November of 1915, it all came together in an extraordinary sprint. Einstein presented a series of 4 papers to the Prussian Academy of Sciences on 4 successive Thursdays, November 4th, 11, 18, and 25, each one refining and correcting the previous one. On November 18th, he showed that his new equations correctly predicted the anomalous precession of Mercury's perihelion, those 43 arcseconds per century that had puzzled astronomers for decades. The equations gave exactly the right answer, with no adjustable parameters, no fudge factors. Einstein later said, his heart palpitated when he saw the result. He was so excited he couldn't sleep. And on November 25th, he presented the final, correct form of his field equations. General relativity was complete. The physicist John Wheeler later summarized the whole theory in one sentence. Spacetime tells matter how to move. Matter tells spacetime how to curve. That's the whole thing. And the equations themselves, in their most condensed form, are beautiful. The Einstein tensor, describing the curvature of spacetime, equals a constant times the stress-energy tensor, describing the distribution of mass and energy. One equation linking geometry and matter. From that equation flows everything: the motion of planets, the bending of light, the slowing of time, the existence of black holes, the expansion of the universe, the rippling of gravitational waves across the cosmos. But the theory needed a dramatic test, a prediction that clearly distinguished it from Newton, and the most obvious candidate was the bending of starlight by the sun. Einstein's theory predicted that starlight passing close to the sun should be deflected by twice the amount that Newtonian gravity would predict. And the man who organized the observation that would test this prediction was Arthur Eddington, a British astrophysicist, a Quaker pacifist, and one of the few people in England who understood Einstein's theory during the war years. Eddington was a remarkable figure in his own right. He was the leading astrophysicist in Britain, the first person to understand and promote Einstein's theory in the English-speaking world, at a time when scientific communication between Britain and Germany was virtually non-existent because of the war. He'd received copies of Einstein's papers through the neutral Netherlands, passed along by the Dutch astronomer Willem de Sitter, and Eddington saw the eclipse expedition as more than just a scientific test. He saw it as an act of international reconciliation. Here was a British scientist, just months after the end of a catastrophic war, traveling halfway around the world to test the theory of a German scientist. Science transcending national borders, proving that the pursuit of truth was bigger than any conflict. The expedition itself was an adventure. Eddington led the team to Principe, a tiny island in the Gulf of Guinea off the coast of West Africa, while a second team, under Andrew Crommelin, went to Sobral in northeastern Brazil. Getting to Principe meant weeks of sea travel. The weather was uncooperative. On the morning of the eclipse, May 29, 1919, it was raining on Principe, and the clouds didn't begin to clear until shortly before totality. Eddington's team managed to take photographs, but many of the plates were useless because of cloud cover. Of the photographs that were usable, the measurements were delicate. They had to compare the positions of stars near the sun during the eclipse with the positions of the same stars photographed months earlier, when the sun was in a different part of the sky, and the displacements they were looking for were tiny. A few arcseconds, less than the width of a needle held at arm's length. The Sobral team had better weather, but their own problems. Their main telescope suffered from a focus issue caused by the heat of the sun just before totality expanding the mirror, and the resulting photographs were slightly blurred. A backup instrument produced better results. When all the data was analyzed back in England, the result favored Einstein. The measured deflection was about 1.75 arcseconds, compared to Einstein's prediction of 1.74 arcseconds and Newton's prediction of 0.87 arcseconds. Close enough. The Royal Society and the Royal Astronomical Society held a joint meeting on November 6, 1919, and the result was announced. The room, according to witnesses, had an almost religious atmosphere. The philosopher, Alfred North Whitehead, who was present, later wrote that there was a sense of drama comparable to a Greek tragedy. The portrait of Newton looked down from the wall on a scene that would forever change his theory's status. The expeditions photographed stars near the sun's disk during the total eclipse of May 29, 1919. When the results were analyzed back in England, The measured deflection matched Einstein's prediction, not Newton's. The announcement came on November 6, 1919, at a joint meeting of the Royal Society and the Royal Astronomical Society in London. The Times of London ran the headline, "Revolution in Science, New Theory of the Universe, Newtonian Ideas Overthrown." Einstein became the most famous scientist in the world overnight. He went to bed unknown outside of physics and woke up a global celebrity. Now, the 1919 measurements had significant uncertainties. The Principe observations suffered from cloud cover, and some of the Sobral photographs were blurry. Later analyses have shown the error bars were large enough that the result was suggestive rather than conclusive by modern standards. But subsequent measurements, during later eclipses, using radio telescopes to observe quasars near the Sun, and especially using space-based observations, have confirmed Einstein's prediction with extraordinary precision. He was right, and the bending of starlight has since become one of the most powerful tools in astronomy. Gravitational lensing, the bending of light from distant galaxies by intervening massive objects, lets astronomers magnify the distant universe, discover exoplanets, and map the distribution of dark matter. Einstein predicted gravitational lensing in 1936, but thought it would never be observed. He was wrong about that. It's now seen routinely. Let's talk about gravitational time dilation, because it affects you right now, in a practical, measurable way. Einstein's theory predicts that time runs at different rates depending on the strength of the gravitational field. The stronger the gravity, the slower time passes. Your feet are slightly closer to the center of the Earth than your head, so time runs very, very slightly more slowly at your feet. Over a lifetime, your feet age about 90 billionths of a second less than your head. In 2010, physicists at the National Institute of Standards and Technology measured this effect between two clocks separated by a height difference of just 33 centimeters, about 1 foot, using aluminum ion clocks, precise enough to detect the difference. The lower clock ran slower, by exactly the amount general relativity predicted. Where this matters in everyday life is GPS. The Global Positioning System uses satellites orbiting about 20,200 kilometers above the surface, each carrying an atomic clock. Your GPS receiver determines your position by comparing time signals from multiple satellites. The satellite clocks are affected by two relativistic effects. Special relativity says they should run about 7 microseconds per day slow because of their orbital speed. General relativity says they should run about 45 microseconds per day fast because they're higher up in the gravitational field. The net effect is about 38 microseconds per day fast. If you didn't correct for this, GPS positions would drift by roughly 10 kilometers per day. The correction is built into the satellites before launch. Einstein's 1915 theory makes your phone's map work. Now let's push into the most extreme territory that Einstein's equations reveal, because some of the most dramatic predictions of general relativity involve gravity at its most intense. Situations where space-time is warped so severely that it does things nobody could have imagined. And let me tell you about neutron stars, because they're one of the most astonishing objects in the universe, and they bridge the gap between the physics we understand and the physics we're still figuring out. When a star between about 8 and 25 solar masses exhausts its nuclear fuel, its core collapses. The electrons are crushed into the protons, forming neutrons, and the entire core, about 1.4 to 2 solar masses of material, is compressed into a ball roughly 12 kilometers across. That's a city-sized object with the mass of the Sun. A teaspoon of neutron star material would weigh about 6 billion tons on Earth. The density is roughly comparable to cramming the entire human population into a sugar cube. Neutron stars were predicted theoretically in 1934 by Walter Baade and Fritz Zwicky. And Zwicky, incidentally, is the same person who first proposed the existence of dark matter based on observations of galaxy clusters. The Crab Nebula, that beautiful glowing cloud of gas in the constellation Taurus, is the remnant of a supernova observed by Chinese and Japanese astronomers in 1054 CE, and at its center is a neutron star spinning 30 times per second, sending out beams of radiation like a cosmic lighthouse. When these spinning neutron stars were first detected as regular pulses of radio waves by Jocelyn Bell Burnell and Anthony Hewish at Cambridge in 1967, the signals were so regular, so precise, so unnatural seeming, that for a brief time they were half-jokingly labeled LGM-1 for Little Green Men. They weren't aliens. They were the universe demonstrating what happens when gravity compresses matter to extremes that make our normal intuitions completely useless. The gravitational field at the surface of a neutron star is about 200 billion times stronger than at the surface of the Earth. Time dilation at the surface is significant. Clocks on a neutron star tick about 20 or 30% slower than clocks far away. Light leaving the surface is significantly redshifted. And the space-time curvature is so extreme that a neutron star effectively lets you see its back. Light from the far side of the star bends around in the curved space-time and reaches your eyes, meaning you can see more than half the surface at once. General relativity at work, distorting even the geometry of vision. Let's talk about black holes. The concept emerged almost immediately after Einstein published his equations. In December 1915, just weeks after the final field equations appeared, Karl Schwarzschild, a German astronomer serving on the Russian front in World War I, calculating artillery trajectories by day and solving Einstein's equations by night, found the first exact solution for the spacetime around a perfectly spherical, non-rotating mass. His solution had a disturbing feature. At a certain radius, now called the Schwarzschild radius, the math went singular. Below that radius, space-time was curved so extremely that nothing, not even light, could escape. For an object with the mass of the Sun, the Schwarzschild radius is about 3 kilometers. For the Earth, about 9 millimeters. Schwarzschild died in 1916, just months after sending his solution to Einstein, from pemphigus, a painful autoimmune skin disease he contracted in the trenches. He was only 42. It's one of those historical tragedies that makes you pause. A man doing some of the most beautiful mathematics in the history of physics, while serving on the front lines of one of the ugliest wars in human history, and dying before he could see the full implications of what he'd found. And for decades, most physicists didn't believe these objects could actually form in nature. Einstein himself published a paper in 1939 arguing against the physical reality of such extreme collapse. But the universe proved more creative than Einstein expected. In the 1930s, Subrahmanyan Chandrasekhar, a young Indian astrophysicist barely 20 years old, working out calculations on a ship from India to England to begin his studies at Cambridge, showed that stars above about 1.4 solar masses couldn't be supported by electron pressure after they exhausted their nuclear fuel. They would collapse further. When Chandrasekhar presented this result to the Royal Astronomical Society, Arthur Eddington, the very same Eddington who had confirmed Einstein's light-bending prediction, publicly ridiculed him. Eddington refused to believe that stars could collapse to such extreme states. It was one of the great misjudgments in the history of science. Chandrasekhar was right. He eventually won the Nobel Prize for this work in 1983, more than 50 years after doing it. For stars that are massive enough, after the supernova explosion blows off the outer layers, If the remaining core exceeds about 3 solar masses, nothing can halt the collapse. Not electron pressure, not neutron pressure, nothing. The core collapses past the Schwarzschild radius, and a black hole forms. All the mass falls inward, past the event horizon, the point of no return, and continues toward the singularity at the center, a point of theoretically infinite density, where Einstein's equations break down. The event horizon itself is extraordinary. It's not a physical surface. You wouldn't feel anything special as you crossed it, if the black hole were massive enough. The tidal forces at the event horizon of a supermassive black hole can be quite gentle. You'd pass through without noticing, but you could never come back. Inside, every possible path leads toward the singularity. Moving away from it becomes as impossible as moving backward in time. For decades, black holes remained theoretical. Then, in the 1960s and 1970s, X-ray telescopes discovered compact objects in binary star systems that were too massive to be neutron stars. Gas spiraling inward from companion stars formed superheated accretion disks, emitting intense X-rays. Cygnus X1, identified in 1972, became the first widely accepted black hole candidate. And then, in April 2019, the Event Horizon Telescope, a planet-spanning network of radio telescopes, captured the first direct image of a black hole's shadow, the supermassive black hole at the center of galaxy M87, about 6.5 billion times the mass of the Sun. The image, that glowing orange ring around a dark void, matched Einstein's predictions with remarkable precision. Equations written on paper in 1915, confirmed by a telescope the size of the Earth over a century later. And then there are gravitational waves. If mass curves spacetime, and if that mass is accelerating, the curvature changes, and those changes ripple outward at the speed of light, like ripples on a pond. Einstein predicted them in 1916, and spent decades going back and forth on whether they were real or mathematical artifacts. They're real. The story of how LIGO came to be is itself an extraordinary saga of persistence. The idea of detecting gravitational waves goes back to the 1960s, when the American physicist Joseph Weber built the first gravitational wave detectors, large aluminum cylinders that would, in theory, vibrate when a gravitational wave passed through. Weber claimed to have detected gravitational waves in 1969, but nobody else could replicate his results, and eventually, the scientific community concluded that his detectors weren't sensitive enough. The signals he reported remain unexplained, but they almost certainly weren't gravitational waves. The idea of using laser interferometry, splitting a laser beam, sending the halves down perpendicular arms, bouncing them off mirrors, and looking for tiny changes in the interference pattern when the arms stretched and compressed differently, was developed in the 1970s by Rainer Weiss at MIT, who worked out the detailed engineering requirements in a landmark 1972 paper. Independently, Kip Thorne at Caltech had been thinking about gravitational waves from the theoretical side and became convinced they could be detected with sufficiently sensitive instruments. Thorne and Weiss joined forces, and eventually Ronald Drever, a Scottish physicist, joined as the third principal investigator. The project took decades, literally decades. The first proposal to the National Science Foundation was in the 1980s. Construction of the LIGO detectors began in 1994. The initial LIGO ran from 2002 to 2010 and detected nothing. It was designed as much to prove the technology as to make a detection. Then came Advanced LIGO, a major upgrade that improved the sensitivity by a factor of about 10, which, because gravitational wave strength falls off with distance, meant it could survey a volume of space about 1,000 times larger. Advanced LIGO began its first observing run in September 2015, and on its very first day of operation, literally the first day the upgraded detectors were turned on, it detected a signal: the merging of two black holes. The timing was almost poetic. A century of waiting, decades of building, and the universe delivered a signal on day one. Weiss, Thorne, and Barry Barish, who had taken over the project's management in 1994 and shepherded it through the funding and construction challenges, were awarded the Nobel Prize in Physics in 2017. It was, by any measure, one of the great experimental achievements in the history of science, detecting a change in the length of a 4-kilometer arm smaller than 1/10,000th the diameter of a proton. On September 14, 2015, almost exactly 100 years after Einstein completed general relativity, the LIGO detectors picked up the signal. Two black holes, about 1.3 billion light-years away, each roughly 30 times the mass of the Sun, spiraling into each other and merging. In the final fraction of a second, they were orbiting each other hundreds of times per second, at about 60% the speed of light. The gravitational waves rippled outward, and 1.3 billion years later, they stretched and compressed LIGO's 4-kilometer arms by about 1,000th the diameter of a proton, the most sensitive distance measurement ever made by humans. And the signal, the characteristic chirp of inspiraling black holes, frequency and amplitude rising together, matched Einstein's equations perfectly. Since then, dozens of gravitational wave events have been detected: merging black holes, merging neutron stars, a neutron star swallowed by a black hole. A new form of astronomy has been born. We can listen to the universe, not just look at it. Every detection tests general relativity in the most extreme conditions imaginable, and every time, the theory holds. But here's where our story pushes toward the frontier, toward the things we don't yet understand. Despite all these triumphs, we know Einstein's theory cannot be the final word. We know this because general relativity and quantum mechanics, the two greatest theories in physics, are fundamentally incompatible. Quantum mechanics describes the subatomic world with breathtaking precision. General relativity describes gravity and the cosmos with equal precision. But when you try to combine them, you get mathematical nonsense. The calculations produce infinities that can't be removed. Usually this doesn't matter, because gravity is so weak at atomic scales that quantum mechanics can ignore it, and spacetime is so smooth at cosmic scales that general relativity can ignore quantum effects. But there are extreme places where both should apply simultaneously. The singularity inside a black hole, where all the mass is compressed to a point, the first instant of the Big Bang, when the entire observable universe was packed into a space smaller than an atom. At these extremes, our theories collide, and our understanding breaks down. The quest for a quantum theory of gravity, a theory that unifies Einstein's geometric gravity with the probabilistic quantum world, is one of the great open problems in physics, pursued for nearly a century, with no complete solution. String theory, which proposes that fundamental particles are actually tiny vibrating strings, naturally includes gravity, but requires extra dimensions and comes in a vast landscape of possible versions. Loop quantum gravity tries to quantize spacetime itself, treating space as a discrete network of tiny loops. Both approaches have produced insights. Neither is complete, and meanwhile, there are observational mysteries that our current theories can't explain. The evidence for dark matter comes from multiple independent lines of observation, which is what makes it so compelling and so frustrating. The first clue came from Fritz Zwicky in 1933. Zwicky measured the velocities of galaxies in the Coma cluster and found that they were moving much too fast to be held together by the gravitational pull of the visible matter alone. The cluster should have flown apart long ago. He concluded that there must be far more mass present than what was visible. Dunkel materia, dark matter. Then, in the 1970s, the American astronomer Vera Rubin made observations that brought the problem into sharp focus. Rubin measured the rotation speeds of stars at various distances from the centers of spiral galaxies. In a galaxy held together by the gravity of visible matter alone, you'd expect stars in the outer regions to orbit more slowly than stars closer in, the same way the outer planets in our solar system orbit more slowly than the inner ones. But Rubin found that the rotation curves were flat. Stars at the edges of galaxies were orbiting just as fast as stars much closer to the center. The only explanation that worked was that the galaxies were embedded in vast halos of invisible mass, dark matter, extending far beyond the visible edges of the galaxy, providing the extra gravitational pull needed to keep the outer stars in their orbits. Rubin's work, done largely with her collaborator Kent Ford, was initially met with skepticism, in part because she was a woman in a field dominated by men, and in part because the conclusion was so strange. But as other astronomers confirmed her results in galaxy after galaxy, and as other lines of evidence converged, the gravitational lensing of galaxy clusters, the cosmic microwave background, the large-scale structure of the universe, dark matter became inescapable. Something out there is exerting gravitational force on a cosmic scale, and we have no idea what it is. Multiple experiments, deep underground detectors shielded from cosmic rays, particle colliders at CERN, space-based gamma-ray telescopes, have searched for dark matter particles. So far, nothing. The mystery remains. Whatever dark matter is, it makes up about 27% of the universe, about 5 times more than all the ordinary matter in every star, planet, gas cloud, and person in the cosmos. And then there's dark energy, arguably even more mysterious. In 1998, 2 teams studying distant supernovae discovered that the expansion of the universe isn't slowing down, it's accelerating. Something is driving this acceleration, a kind of cosmic repulsive effect on the largest scales. We call it dark energy, and it makes up about 68% of the universe's total mass energy content. Ordinary matter, stars, planets, people, everything you can see, is only about 5%. We don't understand the vast majority of the universe. And here's another layer to the mystery. The accelerating expansion means that the ultimate fate of the universe is not what anyone expected. For most of the 20th century, cosmologists assumed that the gravitational pull of all the matter in the universe would gradually slow the expansion down. The question was whether it would slow it enough to stop and reverse, leading to a big crunch, or whether the expansion would continue forever, but always decelerating. Nobody expected the expansion to speed up. That changes everything about the long-term future. In a universe dominated by dark energy, distant galaxies are being carried away from us faster and faster. In the far future, billions of years from now, galaxies beyond our local group will have receded so far and so fast that their light will never reach us. The observable universe will shrink. The sky will go dark, one galaxy at a time. That's a sobering thought, but it's also a deeply beautiful one, the universe giving us a window of cosmic time in which to see it, and then slowly drawing the curtains. Einstein actually anticipated something like dark energy. When he first applied his equations to cosmology in 1917, they predicted a dynamic universe. either expanding or contracting. Uncomfortable with this, he added a term called the cosmological constant to keep the universe static. When Hubble discovered the expansion in 1929, Einstein reportedly called it his biggest blunder and dropped it. But the cosmological constant is back. The simplest explanation for the accelerating expansion is a constant energy density filling all of space, mathematically identical to Einstein's cosmological constant. And here's one of the deepest puzzles in all of physics. When quantum mechanics tries to predict the value of this constant from the energy of the quantum vacuum, the prediction is wrong by about 120 orders of magnitude, not 120%, a factor of 10 to the 120th power. The most spectacularly wrong prediction in science. There's a scale at which these questions become unavoidable, the Planck scale, named after Max Planck, the same physicist who started quantum mechanics with his work on blackbody radiation in 1900. If you combine the three fundamental constants that define quantum mechanics, relativity and gravity, Planck's constant, the speed of light, and the gravitational constant, you can construct a natural length, a natural time, and a natural energy. The Planck length is about 1.6 times 10 to the minus 35 meters. That's incomprehensibly small. It's to an atom what an atom is to the observable universe, roughly speaking. The Planck time is about 5.4 times 10 to the minus 44 seconds, the time it takes light to travel one Planck length. At these scales, the smooth spacetime of general relativity almost certainly gives way to something else, something quantum, something foamy, something where the very notion of space and time as a smooth continuum breaks down. We can't probe the Planck scale experimentally, not even close. The most powerful particle accelerator ever built, the Large Hadron Collider at CERN, probes distances about 1,000 trillion times larger than the Planck length. To directly observe Planck scale physics, you'd need an accelerator roughly the size of the Milky Way galaxy. So for now, the quantum structure of spacetime remains hidden, accessible only through mathematics and theoretical reasoning. But the fact that it exists, the fact that there's a scale at which our best theories of gravity and quantum mechanics must merge, tells us that a deeper theory is out there, waiting to be found. Some physicists think the key is to quantize spacetime itself. That's the approach of loop quantum gravity, which treats space as made of tiny, discrete chunks, like atoms of geometry. Others think the key is to start with quantum mechanics and derive spacetime as something that emerges from more fundamental quantum information. That's the flavor of some recent ideas connecting quantum entanglement to the structure of spacetime, sometimes called ER equals EPR, after a beautiful conjecture by Juan Maldacena and Leonard Susskind. Still others think we need completely new conceptual frameworks that nobody has thought of yet. The honest answer is, we don't know. And that's exciting, not discouraging. The biggest questions are still open. The deepest mystery is still unsolved. Gravity, the first force humans ever noticed. The most obvious fact about the physical world, why things fall down, remains, at its most fundamental level, unexplained. So here we are, lying in the dark, and the honest picture is this. We know an extraordinary amount, and what we know is beautiful. We know that gravity is the curvature of spacetime, that mass tells spacetime how to curve, and spacetime tells mass how to move. We know this so precisely that we can predict the bending of starlight, the orbit of Mercury, the spiraling of black holes, the rippling of gravitational waves across 1 billion light-years, and the timing of GPS satellites to within nanoseconds. And yet we also know it's incomplete. Somewhere, at some scale, general relativity must give way to something deeper, something that unifies gravity with quantum mechanics, something that explains what happens inside black holes and at the first instant of the Big Bang, something that might tell us what dark matter is and why the cosmological constant has the value it does. But there's something wonderful about that. Every generation has found gravity deeper, stranger, and more beautiful than the one before imagined. Aristotle thought things fell because they were seeking their natural place. Galileo showed they all fall the same way, and he gave us the mathematics to describe it. Newton unified the apple and the moon, gave us a universal law that discovered new planets, and yet couldn't explain how gravity crossed empty space. Einstein showed that gravity isn't a force at all, it's the shape of spacetime itself, and his theory predicted black holes, gravitational waves, and the expansion of the universe, all confirmed with extraordinary precision. And whoever comes next will stand on Einstein's shoulders, the way Einstein stood on Newton's, the way Newton stood on Galileo's. That's how understanding works. It doesn't replace itself, it accumulates. Each theory becomes a special case of something deeper. Newton isn't wrong. He's incomplete. Einstein isn't wrong. He's also incomplete. And whatever comes next will contain them both, the way a larger map contains a smaller one. Gravity is still pulling on you right now. It's keeping the air in the room, holding the moon in its orbit, shaping the galaxy you live in. The space-time around you is gently curved by the Earth's mass, and you're lying at the bottom of that curve, and the bed is pushing back, keeping you from falling any further. Time is ticking, just a tiny bit slower at your feet than at your head. Gravitational waves from colliding black holes are passing through you at this very moment, stretching and compressing the space between the atoms of your body by amounts too small to feel, but real enough to measure, with a 4-kilometer interferometer in Louisiana. The same gravity that Galileo studied with bronze balls on wooden boards in Pisa, that Newton captured in an equation elegant enough to fit on a napkin, that Einstein reimagined as the curvature of reality itself. That gravity is right here, right now, doing exactly what it's always done, holding things together, bending paths, shaping the universe, pulling gently, patiently, without ever stopping. And somewhere out there, right now, someone is working on the next piece. Someone is turning the problem over in their mind, the way Newton turned the apple, the way Einstein turned the equivalence principle. They might be a graduate student staring at a blackboard. They might be a young physicist in a lab somewhere, measuring quantum effects so small they barely whisper. They might not have been born yet, but whoever they are, they'll inherit 4 centuries of curiosity and mathematical beauty, and they'll push the understanding one step further, because that's what we do. We look at the universe, we ask how it works, and slowly, patiently, generation by generation, we figure it out. Not all at once, not completely, but always a little more. So let that settle. Let the equations fade. Let the names and the dates blur into the background, the way stars blur when you stop trying to focus on any one of them. What remains is just this. Gravity is here, and it's real, and it's stranger and more beautiful than it looks. And after centuries of asking why things fall, we've gotten answers that are astonishing and incomplete and still unfolding. And right now, it's late, and the gravity that holds you in your bed is the same gravity that holds galaxies together, the same gravity that warps time itself, the same gravity that 14 billion years ago pulled the first atoms toward each other and began the long, slow process of building everything there is. You're made of those atoms. Gravity is still holding you together, still guiding your path through curved space-time, still doing what it does, quietly, patiently, without ever letting go. Rest well,